Today we change the topic completely and move to the world of perhaps one of the most important excitations. These are electron excitations. They're simply electrons living on the lattice. I'm sure you know a lot about the main properties of electrons on the lattice, moving crystalline lattice, periodic structure, and the general properties of the wave functions of the electrons, which are known as the properties of block waves, the block theory. There are many approaches, as you already know, to describe the motion of electrons at a single particle level in a crystalline lattice, and one of those deals with the limit of a weak periodic perturbations, assuming that the kinetic energy of the electrons is very large and the potential is weak. Then you basically what you have this break reflections at the creation of the special points in momentum space when gaps open in the spectrum of free electron, which is a parabolic dispersion, and in certain cases, in certain values of the momentums which satisfy the break condition, gaps open. In this case, the allowed values of the energies which form broad bands, and those bands which are called gaps, the bands of forbidden energies, are small, are narrow. So the effect is small, therefore the gap is small. There is another approach when instead of this picture you assume that the most of the time electrons spend on their own atoms they originate from. And from time to time they undergo hopping or tunneling from one potential well to the other. So what I have in mind is the following picture. Suppose your potential looks like a sequence of potential, your periodic potential looks like a sequence of potential wells. You can assume that you have a level in each potential, or levels, maybe more than one, which may or may not be degenerate with respect to other degrees of other quantum numbers, such as the orbital degree of freedom. In the simplest case, you assume there is only one, this is a theoretical model, only one state in the band, which is non-degenerate. The only degeneracy is associated with the spin. This is the simplest possible picture. Right? So most of the time, if you assume that this barrier separating two neighboring wells is very, very high and sufficiently broad, then at zero order, in the zero approximation, you simply assume that this barrier is impenetrable. You cannot, the particle cannot go from one well to another well. You simply ignore it completely, and then you have a collection of independent potential wells, completely disconnected from each other. You cannot hop from one to another. And you have then, if you put an electron in one electron in this gap, in this potential well, you can also put it here, or here, and then you will get a n-fold degeneracy for a single electron state on such a lattice, depending on the number of possibilities that you have. Right? You can, if you take in the spin into account, you will, instead of 2n, you will get 2. Instead of n, you will get 2n. 2 extra 2 coming from the spin degeneracy. So all the time, each of such state would be a stationary state, infinitely long-living. Nothing dramatic would happen. But now if you assume that however wide the potential or potential barrier is, and however high it is, there is still a finite possibility for a particle to undergo a quantum tunneling between the nearby states, and then the particle can hop from this state to this state. And that's already a mechanism of creating of a quasi-particle. Because by saying a quasi-particle, I mean that the particle has acquired a degree of freedom which allows it to be transferred from one point to another one. It gets delocalized. It does spend most of the time in the corresponding potential well, but from time to time, not very frequently. It's a rare process. Random, not the random, it's quite a coherent process, but it's not it doesn't happen very often, so to speak. The particle spends most of the time in its potential well. So how should you proceed? Suppose you take a certain potential well, ignore all the others, assuming the electron, nothing dramatic happens to it, and you solve the Schrödinger equation, which is something like minus h squared by 2 masses, nabla squared and plus mu, x minus a n naught. This is the site number n, right? Now this is the site number n plus 1. This is the equation that you solve, x minus n a naught is equal to energy. I deliberately subtract. I could have written here nothing, just 0, nothing. Then it would be the site, the central site at the origin, with n equal to 0. But it can be any site. This is why I put this arbitrary here. So you solve this, and this is a kind of your atomic orbital function corresponding to electron state in the isolated potential one. All right. Now, as I said, not by chance that a single electron can be distributed in each of these, can be placed in each of these n potential wells, and therefore its state is n-fold degenerate. Right? Every time when you have in quantum mechanics a problem with degeneracy, the first thing you do, you write down the wave function as a linear superposition of the degenerate wave functions. This is the first thing you do, right? If you recall the situation, for instance, with the double well potential, that's precisely what you do there. You build up a superposition of the particle states in the left band, in the left potential, the right band. So you can try to do the following thing. You can write down the wave function as a superposition of your atomic orbitals. And since all those states are completely equivalent, the only difference they can experience is the phase factor. And the phase factor can be written like this. So if I replace all the notations from one-dimensional to three-dimensional or n-dimensional, this is a scalar product, k times n as the radius vector, and 1, A1. These are basis vectors, N2, A2, and so forth. It can be N3, A3 in three-dimensional space by having to go further. For a d-dimensional space, it's fine. But here I have to write down this k, a vector, and then general theorems of which you are aware advise me that I should treat k almost as a momentum, almost, but not exactly. And the difference is that on the lattice there is no notion of a momentum in the usual sense, because the lattice does not have translation invariance of empty space. And this, the fact that the momentum is a well-defined quantum number follows from its consideration. So on the lattice, the momentum of a particle is not conserved because the periodic lattice does not have the symmetry of empty space. So this is a so-called quasi-momentum. The quasi-momentum which differs from the momentum by the fact that the values of k and k plus g, when g is the reciprocal lattice vector, are physically equivalent. And therefore, the whole theory must be periodic with respect to the shift of k by this vector. The energy, the band energy, whatever. Any excitation will be characterized by energy which is periodic function of k. So if we take this point of view that we can treat this as an attempt to build up what is called the block wave, and this is would be the first step in building up a well-defined theory, because this is a linear combination of degenerate wave functions centered at different points. Right? So the block theorem, to check whether it's satisfied or not, I have to perform a translation by some lattice vector n. And if I do, I will obtain something like this. It will be phi naught r plus n minus n. Since I'm summing over all n, I can simply change the notation. I can introduce n prime, which is n minus n, and then I will get n exponent ak n prime plus n, phi naught r minus n prime. And here I can see that I can push this exponent I k dot n outside the sum, and what remains is just the psi k of r. This is the derivation of the block theorem. Indeed, this is a block wave function which satisfies the standard, the most important condition. A translation by lattice spacing, by lattice vector, effectively multiplies the wave function by this phase factor. In mathematics, this follows under the name that all irreducible representation of an abelian group are one-dimensional. And this is the realization of this thing. So it's a simple physical thing, which has very, very deep mathematical roots, so to speak. So that's fine. The question is, why don't we use this representation to develop, say, a second quantized formalism? We will try, because it's very appealing, because I can then introduce the creation of annihilation operators for the electrons localized at the site n. But to do so, I have to have what? I have to have a field operator, which you must be aware from the course of second quantization, which I must be able to expand in a Fourier series on one hand. Okay, let me write down the block K of R. This is the block function. Oh, let me put it bar. It's better. Okay, over there. This is one possibility. And the other possibility must be something like this. Cn. And looking at what is written there, we'll write down R minus F. Very natural, right? And the connection between these two functions would be this. Now here you have to choose which algebra is defined first. The algebra of the creation annihilation operators in momentum representation and in real space representation. Suppose you chose to define algebra according to the block theorem, because block theorem assumes that the wave functions are characterized by such a quantum number as a quasi-moment. And you will write down this is delta k right? And of course you have to add something like this. And now the good question is, how do you know that in the real space representation, your operators would satisfy a similar algebra? Because if they don't, then forget about the statement of the problem and throw it into the basket and change their profession. You are not good anymore to do physics. Any transformation must be canonical. That means preserving the algebra of basic operators. If this algebra is not preserved, and it's a very easy task, that if there is a transformation from this C-numbered function to this C-numbered function, as it's shown here, then it should be dependent on the orthonormality of the set of these functions and these functions to assume that one algebra leads to the second one. It's very much close to the fact that if you have a Hermitian operator and built up its eigenfunctions and eigenvalues, then necessarily the set of eigenfunction, eigenstates forms a complete set of orthonormal states. This is absolutely compulsory. But these functions cannot be orthonormal. First of all, they cannot be orthogonal at all. Two functions centered here and here cannot be orthogonal. Because for each potential well, the wave functions can be chosen to be real and even positive if you wish. You can choose the ground state wave function. It will be an assertion. It doesn't have nodes, as you know. The sign will be fixed. And such functions will always have a finite overlap, and there is no chance to make this overlap zero. Which means this cannot be a good choice, because there is no orthogonality for such functions. Never. It doesn't work. It's not true. Even when n is not equal to m, this integral is now zero because both of them are positive, definitely. So you need to have this oscillatory tails. Each wave functions must be very similar to the atomic function, to the atomic orbital, close enough to a given point. So this is a given point. This is the point when your potential well is located, right? So your wave function should follow more or less the profile of the atomic orbital, but otherwise it has to decay with distance according to some law, but necessarily be sign alternating. Because this changes from plus to minus are required to have a chance to annihilate this integral. And these wave functions, these functions are known as one-year functions. So there are block functions, these are block functions, these are block functions. And here are the so-called one-year functions. So we very often use this language. This is an electron in a given atomic state. It's not quite so. It's an electron in a given Wannier state, which is very similar to the localized atomic state at the point N, but otherwise it has a, all those extra features which make it different. But now we are on the same ground. This algebra is related because now I can indeed associate the block wave 1 over square root of n as usual sum over k exponent I to n WR minus n, or I can reverse it. This is a perfectly unitary transformation, 1 over n, sum over up. It should be n here, and it should be k here. Minus I k n, and the block wave. This is an invertible transformation. Everything is fine. The sum over works. And I can choose any basis, the basis of these states or the basis of these states, depending on the type of. Well, this is a kind of a few words about the background. I will not talk too much about the details. So, let me again draw the lattice. For simplicity, I will draw a one-dimensional lattice. I will assume that there is an energy epsilon n which is equal to epsilon 0. It does not depend on n. It's the same for each lattice site, which is nothing but the energy level. The electron bound in in a respective potential one. And the first thing I can write down for the Hamiltonian is epsilon naught sum over n, since we have electrons with a spin, sigma, C and sigma dagger, C and sigma. This is the one-year representation. N is the lattice site, but then understand that it's more accurately it's a one-year state with all the properties we have already outlined and discussed. We will blindly assume that this is the electron localized at the end side. Its wave function nevertheless has its tails, which is inevitable, right? If I have only this, that means that I have nothing, because it's not a problem. It's simply a statement of the fact that the electron has, its location can be arbitrary in each potential. Well, I can localize it anywhere. Every time I localize it, I immediately build up the occupation number operator, and then I can look at the possible configuration, understanding that for each value of the spin, with a fixed n, I may have a configuration n up equal to n down equal to 0. That means that I have nothing at the given lattice site, no electrons whatsoever. Or I have n up is 1, n minus n down is 0, or n up is 0, n down is 1. This is precisely the case of one electron on the lattice site with some spin projection, either up or down. And finally, what I have is the configuration of both of them on 1. So the total number of electrons on the given site is 2. And so I have 4 possible configurations. At the given lattice site, I can put 0 number of electrons, 2 number of electrons, or 1 number of electrons. In the lattice case, I have this degeneracy spin after spin. These 4 states form the basis of the so-called Fock space. And the Fock space of a single electron on the lattice site is 4-dimensional because we have 4 mutually orthogonal states. So you can write down the states by indicating eigenvalues of the corresponding operators. So you have 0, 0, 1, 0, 0, 1, and 1, 1. And that's the basis states. It's a well-defined, complete set of mutually orthogonal states, orthonormal states. Well, what is written here is it's the total particle number operator, nothing else. It's epsilon naught times the number of electrons, the operator, which measures the total number of electrons. Then of course, if I have only this, it's a trivial problem. I simply have to distribute in all possible combinatorial ways the given number of electrons among the given number of lattice sites, and then announce the possible energy levels. In any case, the total particle number is a good quantum number is concerned. Please notice that the energy is here, and no one precludes me from saying that let this energy to be V0. Why? Because the total particle number is conserved anyway. This quantity doesn't describe any dynamics. There is no motion of the particles as long as only this is present in the homothenon. It only measures the energies of configurations, which don't play much role. You can measure this energy from any point. For instance, you can measure it from 0. To bring some new flavor to this problem, what you do is you take into account the fact that if you have an electron in this potential well, it can hop either to the right or to the left. By saying right and left, I have in mind the one-dimensional situation, but generally speaking, I'm maybe a multi-dimensional situation. And the hopping represents a tunneling process, and the tunneling occurs because of the overlap of the wave function centered on the lattice sites. And of course, the whole point is that this tunneling is small. Is a weak process, so to speak. So if this is the site n, and this is the site n plus 1, then bringing electron from here to here means kill electron at this point and create electron at that point. So therefore it will be something like minus t, t is the amplitude, Cn plus 1, sigma dagger, C and sigma. For one-dimensional lattice, this process which I described will look like this. Sigma is the same, unless because I didn't assume that there are some kind of spin degrees of freedom playing a role in the dynamics. There is no spin orbital coupling. The spin doesn't undergo flipping. So the orbital motion, the translational motion, is completely disentangled from the spin degrees of freedom. And the general SU2 invariance requires that the spin must be conserved. Spin orbit breaks SU2 invariance, right? Well, this cannot be the end of the story because I have to add the complex conjugate term, Hermitian conjugate term, which would be T star, Cn sigma dagger, Cn plus 1 sigma. And this is a beta situation. And then I have to sum over all the sites and over the spins. And that's exactly what makes the model interesting. Because only with this, there is nothing to discuss. This is the new issue. Because it describes delocalization of the electrons. Electron can hop from a given site to a neighboring one. In the reciprocal, it could hop on a further hops for the sides, but I assume that the overlap of the wave function is so small that those processes can be neglected. Well, there is a simple exercise you can find. Sure, you can prove that by choosing a proper phases of the C operators, which do not alter, do not modify this algebra. You can always assume that the T, the amplitude T, is a real number. You can fix the phase. It's up to you. More generally, if you look into one of the good textbooks, for instance, like Ashcroft and Merrill on condensed on solid state physics, then you will find that in the formalism of the one-year functions, the derivation of the Hamiltonian, this term will be derived from first principles. So some details, important details can be found there. So I urge you to refresh your memories and to look into that book. But to us, elementary considerations would be fine. So I can therefore put this minus t in front, keep this with the plus sign, and erase all the rest. That's our Hamiltonian, generally speaking. So therefore, the total Hamiltonian, if you wish, is this term plus this term. But now I said that since total, by the way, yes, that's important thing. This Hamiltonian, of course, this Hamiltonian is called the tunneling or hopping part of the Hamiltonian. It commutes with the total particle number. Because the particle, when the particle can delocalize, it doesn't disappear. There is no drains and catches. So, there is no possibility to eliminate particles. So they're conserved. They can be redistributed. So this particle number is conserved. Therefore, for the purpose of this Hamiltonian, this doesn't play a role. So once you fix the number of particles, number of electrons, you can fix it one and for all. This quantity will be a given number, and you are not interested in it anymore. So that's your Hamiltonian. It's a one-dimensional version. This is H. Now, just similar to what we have for the transformation between the Bloch waves and momentum representation, linear functions, and real space representation, you can immediately derive the corresponding expansion of the operator, second quantized operator, in terms of the operators that create Bloch waves. So what you can do, you can write down 1 over square root of n, sum over k, this exponent, I k n, and ck. And a similar expression for the conjugate. For the conjugate, you will have to put the minus sign and deduct it there. And you could check that this is consistent with the requirement that the two algebras are satisfied. Well, I'm not going to discuss, for instance, how the total particle number is transformed. We have been discussing this point many times. Who can tell me what shall I write here in momentum representation? Suppose I want to pass from the one-year representation to the Bloch representation. What shall I write down there? We have already discussed more than once. Now, this is why I insist that you have to participate. Your suggestions, what shall I write down here? Okay. Same K? Or double sum, K prime? What? The same? Why are you so sure?
Because K and K prime belong to the flat element
Because what?
The K and K prime would belong to different Hilbert spaces and then they will not communicate.
Okay, well, this is one explanation. More accurately, if we eliminate such a word as a communication, because it's a little bit non-scientific, to be quite honest. Because it's a trace. It's a trace. And this is a unitary transformation. And the trace is invariant under the ternary transformation. Full stop. Appunto. Nothing to discuss. Okay. But now we have a more complicated structure. Suppose this one. What to do with this? This is a simple task to follow. Double sum kk prime, of course. Sigma, if you wish. Ck dagger ck prime. One from here, the other from here. Now you have a sum over n, and you have minus I k times n. People, you must have told me that either I do one-dimensional physics or I do three-dimensional physics. Please eliminate these vectors once and for all. You will do this vectoring exercise for yourselves. All the k's are one-dimensional k's. Okay. I k prime n plus 1. So I push this I k prime outside by writing down n plus 1, I assume that everything has to be multiplied by a naught, of course. By a naught. And then I am left with 1 over n times the sum over n. I minus k plus k prime and a naught. And we know that this is delta k prime. It's some rule. Correct? So therefore, 1 over n times the sum gives me delta k. From the canonical, I'm left with only one summation over k. I have ck dagger ck. And instead of this one, I write down simply I, k, and naught. This is for this term. But it's also a conjugate term, the Hermitian conjugate, which will keep this operator part intact, only add a conjugate exponent. And sum of these two exponents will give me twice the cosine. This is why, in momentum representation, this Hamiltonian requires a very simple form. Requires a very, very simple form. It is sum over k over sigma, epsilon of k, ck sigma dagger ck sigma, and epsilon of k is minus twice t and cosine k. So you see, it's your problem of electron hopping is diagonalized using elementary tricks, just a standard Fourier transformation. And the spectrum is a simple cosine. The spectrum is a periodic function. This is k. I will measure it in units of inverse a naught, pi, minus pi, pi by 2, for t positive, epsilon of k, what I have in this picture is the minus cosine, basically. This is what you have. This is your epsilon of k. This is your epsilon of k. And of course, this dispersion is periodic. If I go along larger values of k, it will be periodist. So all physically inequivalent states are located inside this brilliant zone. This is the brilliant zone. The interval is the brilliant zone. The number of quantized sites in this brilliant zone is exactly n, when n is the number of lattice sites, one-dimensional sites. You know the derivation. And now the rest depends on how many electrons I have. I have to build up the ground state, right? So I start filling the states from below. This is the negative part of the spectrum. This is the positive part of the spectrum. I start filling all the states until I'm exhausted, until I'm left with no more electrons. Suppose up to this point I can fill them, and then all the states are occupied, and we occupy the states according to the Pauli principle. In each state with a given k, I can place two electrons, one spin up and the other spin down. And this is exactly the way I built up the ground state. This is the value of what is called the Fermi energy, or if you wish, this is the value of the chemical potential at zero temperature. It can be even here, it can be here, it can even reach the top of the band. When the band is empty, it's an insulator because there are no electrons. When the band is completely filled, it's again an insulator because there are no free states to move, because Pauli principle precludes such a state from being deformed to go from, there is no excitations. And of course what is shown here is extremely far from reality. There is no such thing as a single band. There are some should be bands well below and well above. We simply considered only one orbital state here. There may be some other states. Well, they may be, the spectrum may indeed be bounded from below in principle, but it cannot be bounded from above, and then eventually you go to the limit of the continuous spectrum and will be transformed to a continuous spectrum. That is a difference. Quite often, people switch from canonical ensemble to what is called the Grand Canonical ensemble. The Grand Canonical ensemble is the ensemble when the independent thermodynamic variable is not the particle number, as we suggest here, but rather it is a chemical potential, is the chemical potential. So it depends on the point of view. What is primary? What is the independent variable? When the chemical potential is an independent parameter, independent variable, and the particle number is a function of it, then you have to explicitly put the chemical potential term into the Hamiltonian because it couples to the total electron number. Therefore, it is minus mu sum over k sigma, ck sigma, dagger ck sigma. Now, looking at what I have here, if I build up this difference, if I subtract the chemical potential term from the Hamiltonian of the tight binding model, this is what is called, I should have said, tight binding model, I will get summation over k and sigma, c arc psi k, ck sigma, ck sigma, where psi of k is this energy, tight binding model energy, from which I subtract the chemical potential, measured from the chemical potential. So in this model, the particle number is not fixed. The chemical potential is. What is important about such a representation? In such a representation, the important fact is that I can consider, as you know, when you have Fermi statistics, which defines the ground state as the multitude of all states filled twice within some interval between minus k Fermi and plus k Fermi. In other words, there is a window of momenta between the 2 points. This point is called the Fermi momentum. This is exactly the point which separates the field states from empty space states. You know an example of this kind from a three-dimensional model of free electrons. This is very much similar to what is there. The only difference is that first, the electrons are not free. These are band electrons. Band electrons means that this is the excitations in the crystalline lattice, which are not exactly the same as free electrons in the vacuum. And the second point is that this is in this specific case, it's a one-dimensional problem. If this problem were a three-dimensional, nevertheless, you wouldn't reach the picture that you are accustomed to in the three-dimensional ideal Fermi gas. Why? Because in the three-dimensional ideal Fermi gas, your Fermi surface represents a sphere. The spectrum is isotropic. On the lattice, the spectrum is not isotropic, generally speaking. It has the symmetry of the lattice, and the symmetry of the lattice is lower than the symmetry of empty space, which is rotational invariant and things like this. So therefore, there should be differences. The Fermi surface may not be as simple as for free electrons. It may not coincide with the, and does not coincide generally with a sphere or any similar geometric figure, but still has a property that it represents a clear boundary, very strict boundary, which separates the field states from the empty states. So there is such an object like a very strange but very important quantum object like a Fermi sphere or Fermi sphere-like thing. In our case, this is just this interval of momenta, where all the states are filled. Outside, all the states are empty. Now, if you want to build an elementary excitation, so let me show only a part of this diagram, of this curve, which is filled. And this is the Fermi energy, or the chemical potential at zero energy. To build an elementary excitation, I have to take a particle from here and bring it somewhere here, or bring it somewhere here, leaving a hole here. At the place when I left a hole, the effective charge is plus E. The hole carries the positive charge. Because to eliminate hole, you have to fill this hole with the electron. Therefore, electron neutrality assumes that the hole carries the positive charge. And this is the true electron with a negative charge, which is here or here. And you can see that these electrons in holes, and this is a general property of any Fermi system with a Fermi sphere, can be created and annihilated only in pairs. It cannot be. Otherwise, you have to add from outside an electron or take an electron deliberately and throw out somewhere. The problem with the conserved particle number, the system with the conserved particle number, only contains excitations when the particles in holes appear and disappear in pairs. Very frequently people say that this is a topological restriction. I will try to avoid such a definition, even though I agree with that. Yeah. So, but once a particle and the hole are created, nothing precludes me to consider this particle in isolation and ask myself what happens to it. I can follow its trajectory. We come to mechanics. I can't follow its trajectory, but I can follow the evolution of its state, I can follow its interaction with some other degrees of freedom. After all, I know that such excitation does not form a bound state with this excitation. These are just plane wave-like states which go to infinity from each other. So therefore, I have to have an opportunity to describe each of them separately. And I can only do that when I use this picture. If I subtract the chemical potential, how can I see it? If I have a Fermi sea completely filled, no excitations whatsoever, when I say a word, when I pronounce a word, let me build up an excited state, that means that I have to increase the energy. The ground state energy is the minimal energy state, its energy cannot be further decreased. It's once and for all is what it is. I can only increase the state of the system, energy of the system, if I build up excitation. So, therefore, both electrons and holes, each of them, must represent elementary excitations with positive excitation energy. Positive. You know, you can imagine, look, everything what is shown here occurs in the negative part of the energy scale, but that doesn't matter. That doesn't affect any physics. The excitation energy must be positive, by definition. Otherwise, your vacuum is unstable. How to see it? To see it, you can do the following. You simply look at this formula more accurately and ask yourself, how can I write down the excitation energy for a particle here and the hole here? Suppose the particle occupies the state K1 and the hole K2, right? So therefore, now what I do, I will build up the excitation Hamiltonian as the Hamiltonian given like this, minus the Hamiltonian of the ground state. And this will give me summation over K, summation over sigma, psi K. Let me directly go from the Hamiltonian just to the energies. And then I will have what? I will have nk sigma minus a can sigma 0. I will call this quantities delta nk sigma, the change in the occupation number of the corresponding states. Right? You must agree with me. What is written here is the difference between given energy of the energy of excited states and the ground states energy. Now for this particle, so there are actually only two terms contributing, let alone the spins. I'm not interested in them. Suppose the spins are just the same, but therefore, for a particle at k equal to k1, sigma, this delta n is 1. Because this state was empty in the beginning, and I filled it with one particle. So therefore, delta n, K1 is plus 1. On the other hand, the change of the occupation number in the second state, K2 sigma, is minus 1. Because this state, K2 state, the K2 state, was filled, and I eliminated it, right? So therefore, what I have here will look like psi K1 minus psi K2. But psi as the energy measured from the Fermi energy. From a state which is above Fermi energy, this quantity is positive. But the energy psi for the whole, without minus, is negative. But with the minus, it is also positive. So you see, this is the excitation energy. Psi of K1 is the excitation energy of the particle. And minus psi K2 is the excitation energy of the hole. Each of them is positive. So therefore, I correctly built up the two-parameter excitation in my system, which is described in terms of the particle of the whole, each of them having positive definite excitation energy. This is the meaning of the passage from epsilon to psi. Every time you measure from the chemical potential, you are on the same ground. You know how to deal with the excitations. Okay, so what else should I say about all this? Okay. Recall, yes. Now a few words about the meaning of this formula, this very formula. It's an important thing, and we have to understand it. It's in much detail. Let me again come back to the problem of a well-known problem of a double well potential, when we have a potential well 1 and potential well 2, and the state localized in this potential well, the state localized in that potential well. And then we also have a tunneling process which couples the two states together. And we know that if epsilon naught is the energy of each of the states and T is the amplitude of the tunneling, then the spectrum E plus minus is epsilon naught plus minus T. So what happens actually, I have a state again, a state another one, and what I have in the end is the splitting of these two states into E minus, E plus, and E minus. What happens? When there is no hopping, when there is no tunneling between the states belonging to different potential wells, your spectrum is doubly degenerate. Whether you put a particle in this potential well or in that potential, it doesn't matter. The energy is the same. When you switch on the perturbation, and the perturbation is the hopping process, the tunneling process, between the well, this degeneracy splits and you have two levels. This is what is called in quantum mechanics a level repulsion. Every time you have degeneracy and there is a perturbation which mixes up these states, the energy splits. Now let's compare this with this situation. Think of only one electron. This electron can be placed either here or here or here or here and fall the degenerate level. So I measure the energy here. I know that the energy level is epsilon naught, even though I have thrown it out, it doesn't matter. This is the n-fold degenerate level, n-fold degenerate level. And this happens at t equals to 0, when t is the hopping amplitude. In the limit when the barrier is huge. Now I switch on this t. This n-fold configuration degeneracy is removed and the band is formed. Look at the band. It consists of these levels, right? Which cover the whole range from 2t to minus 2t. So I have a picture like this. This is 2t, and this is minus 2t, and these are the new levels. And this is what is called the formation of conduction band, right? I created a conduction band. How many states I have? Exactly the same amount as the degree of degeneracy on this level. So this level, being originally n-fold degenerate, unfolded and led to the formation of the broad band. This is exactly of the same origin as the nature of this problem. It's simply the degree of degeneracy here is 2 and here is n. But the essence, the physics, the underlying mechanism is the same. It's a removal of the degeneracy. Your original wave function was a linear combination of the 2 wave functions. The original wave function in this problem is a linear, as I wrote in the beginning, not in the right way, but still, it was not far from reality. It was this, as you remember, the atomic orbital r minus n. It's a linear combination of n localized wave functions. The same stuff. Absolutely. Instead of plus minus, symmetric, antisymmetric, here you write down this exponents. Well, because quantum mechanics of n-fold degenerate bell is different from quantum mechanics of twice double degenerate. So this is the mechanism of formation of the band. This we have already discussed. So now a few general properties of such a model. So you see this is this profile, this band, this looks quite symmetric. If you shift it by a half the width of the Brillouin zone, instead of instead of the minus cosine, we will have simply cosine. Now, instead of cosine, we will have a minus cosine. Doesn't matter as it is. If you shift it by one half of the previous one, by pi, you will get this one, which is equivalent to inverting the sign of epsilon. So there should be some kind of particle-hole symmetry, right? When you overturn the spectrum from cosine to minus cosine, some kind of particle-hole symmetry. How to visualize it? How to find it? We may ask a very general question. What kind of transformation should we apply to find out whether the particle-hole symmetry is present or not? So our Hamiltonian is this one, h minus mu, and let me call it h bar. It's defined as sum over n over sigma minus mu, c and sigma dagger c and sigma, and minus t, c and dagger sigma c n plus 1, sigma plus addition conjugate. That's the Hamiltonian. It is passed from the particle to a hole using this prescription. With your permission, I will put here this coefficient. We will clarify its meaning just within a second, within a minute. A phase, so I go from annihilation operator to a creation operator, but in front, I put a phase factor, which is inhomogeneous, it depends on n, and simply oscillates with the latest side number, transforming to 1 for even sides and minus 1 to odd sides. Why do I do that? We know that in momentum representation, what is written here is summation over k over sigma. Here I have minus mu. Okay, let me write it down as it is. It's twice t minus twice t cosine k a naught plus mu. All right? That's ck sigma. Ck sigma. This is the momentum representation of what is written here. Why do I need this one? If I make the same transformation in momentum space, I will find out that Ck sigma, our momentum representation, goes to Ck plus Q large sigma dagger, and Q large is the quantity which is pi divided by 8. Is this distance. 1/2 of the brilliant zone. It's half a period of the brilliant zone. Twice Q is a reciprocal lattice vector. It's 1/2 of that. Now let us start from here. If I do this transformation, I will obtain minus K sigma. I keep this value. Here I will have Ck plus Q sigma and Ck plus Q dagger sigma, right? That's fine. Which will give me minus summation over K over sigma twice T cosine K A naught plus mu times nothing, because I would like to write it down as 1 minus the same expression. It will be plus 1 minus, no, it will be 1 minus, yes, 1 minus plus sum over K sigma twice T cosine K naught plus mu Ck plus Q sigma Ck plus Q.
Shouldn't it be minus sign?
What?
Shouldn't it be minus sign?
Here? No, because C dagger is 1 minus C dagger C.
Ah, yeah, it's Fermi Energy.
Yeah. So, first of all, you see that this vanishes, because summation over all K of the cosine gives you 0, for different clear reasons. This will give you minus mu times 2 times the number of lattice sides, a constant, which is not a big deal. You can tolerate such things, because they don't contain operators. It's a shifts by energy. But even that will be taken care of. Here I have to, the notion of the brilliant zone means only one thing. The momentum K must belong to the interval, any interval, AB, such that B minus A is 2 pi divided by AB. This is what the block theory prescribes. In momentum space, 2 pi periodicity, and 2 pi is the reciprocal lattice vector, assumes that any 2 points can be chosen as the boundary, provided that the length of the interval is 2 pi. From minus pi to pi, it's a symmetric choice. You can easily choose from 0 to 2 pi. It depends on the school of thought, on your temper when you wake up in the morning and you are in the mood, or you are not in the mood to work in this or that representation. It's up to you. So therefore, I can make a shift. I can write down K plus Q as pi, when pi is a new pseudo-vector, also belonging to the brilliant zone, but the brilliant zone will be shifted with respect to right? So therefore, this will transform to CP dagger sigma CP sigma. This will be just a standard piece. But here, I would have to change K plus Q or K minus Q. That will be a shift by Q. But under this shift, the cosine changes itself. Right? Is it clear? So therefore, I will put the minus sign to change this, what is written. But also, since nothing happens to mu, I will put the minus sign here. And now I'm asking you, what's the difference between this expression and this expression? And the difference is this. So this kinetic energy part is correctly reproduced with its sign. But the chemical potential part, chemical potential changes its sign on the particle Hall transformation. So this is a particle Hall transformation. Particle Hall transformation. Kinetic energy, roughly speaking, T goes to T, but mu goes to minus P. Conclusion. The particle Hall symmetry only takes place for zero chemical potential, which is quite natural, because when the chemical potential goes here just in the middle, then by shifting the whole picture by half a period, you recover the original picture. It doesn't matter. Full symmetry between particles and holes, between those states which are filled and those states which are empty. So therefore, we should remember that mu equal to 0 is a particle Hall symmetric point of the spectrum. And here is the problem I can immediately suggest it to you, even though it is kind of extracurricular problem, which is not part of my course, but maybe a part of some other course which you have already taken or are taking now. Do you remember the statistics of the ideal Fermi gas? You have a Fermi gas and you calculate its thermodynamics. At lower temperatures, using the Fermi distribution function, you can calculate the free energy, you can calculate the specific heat, you can calculate God knows what. Suppose you can calculate Pauli paramagnetism, right? Or any other quantity. You have to do the last integration will be integration over energies with the distribution function, with the Fermi distribution function, or better to have not the Fermi distribution function, but its derivative. Because the Fermi distribution function has a step-like function, whereas the derivative is a delta function. But then you take a serious book, suppose a Landau-Lifshitz course in statistical physics or any other course. And then you find out that for the ideal Fermi gas, the ideal Fermi gas is the gas whose energy is k squared divided by 2 masses. It's quadratic, parabolic dispersion. For such ideal Fermi gas, the chemical potential does depend on the temperature. And the temperature requires the correction of the order of T squared. Again, the chemical potential is a quantity which depends on the temperature. And it is, if you take some value, switching on the temperature with the parabolic dispersion for the electron energy, it will start moving downwards. Right? Now, if you are a consistent theorist, you will say, okay, the parabolic dispersion is not only this part of the spectrum. For instance, if the filling of my band is very, very inessential, a very small number of particles I have in my disposal, I can expand this cosine spectrum, and small k is, again, k squared. So the physics must be very similar. So mechanical potential will be somewhere here. Applying that argument, I would say if I switch on the temperature, the chemical potential will start moving down a little bit. Because this is exactly what the theory of a free electron gas tells me with the parabolic spectrum. But imagine that I have a hole-like situation when my band is almost the band of an insulator. It is almost filled except for a narrow slice of states close to the top of the band. And these are just the holes which are located there. And for the holes, the spectrum is this one. It's minus k squared. Perhaps did you have a course on the physics of semiconductors? You did or you didn't?
No, I did.
You did. Okay. Do you know the difference between the electrons and holes and the hole-like superconductor, particle-like, electron-like superconductor? It's I've said semiconductor. I'm very sorry, semiconductor. I mean semiconductor. Well, you just you must be aware of the fact that your spectrum may have such a structure. There is a conduction band and there is a valence band. In a semiconductor with a small gap, all the states here are filled, all the states they are empty. When you take a state from here and bring here, the spectrum of this one is more or less parabolic with the plus sign. The spectrum of this one is also parabolic but with the minus sign. Its effective mass is negative. Have you ever heard it? About the negative effective masses in solid state systems, like semiconductors. And it's an example. If you are almost filled, you can, this is just a trivial thing, but if you expand cosine in small values of its argument, it's minus x squared divided by 2 cosine of x, right? But with minus cosine, we'll get the plus correction. In other words, the chemical potential, if it's here, if I change the temperature, it will start going upward. So the chemical potential goes downward and goes upwards if the band filling is here. The question is what happens if the chemical potential is 0 in the beginning? And then you switch on the temperature. What happens to it? You see, it's an intermediate point, it's a transition point from the spectrum like this to the spectrum like this. It's something when the topology of the spectrum changes. The system cannot decide where to push the chemical potential, upwards or downwards. And the answer is the chemical potential is not a function of the temperature at all, if the condition of particle-hole symmetry is present. In particle-hole symmetric situations, the chemical potential does not depend on the temperature. So what you can do, you take this model, for instance, you fix the value of the chemical potential 0, to be 0, and you calculate thermodynamics. And you try to calculate the temperature dependence of the chemical potential. And if you correctly do it, you will find out a direct proof that the derivative, d mu dt, the derivative of the chemical potential by the temperature is equal to 0. Since its initial value is 0, it should stay 0 all the way. So it's a kind of exercise for you when you have some time to think about it. All right, so if this minus 1 to the power of n this is the, you must have realized it because of the relationship when you write down I, k, n, suppose ck, and you put the minus 1 to the power of n inside, the minus 1 to the power of n is I, p, and p is just precisely this vector q. Therefore, k is shifted by q, and this is why the shift must be present there. So what we will do next time, unfortunately we are coming out of the schedule a little bit, we will consider a lattice which consists of 2 different atoms. This type of a lattice. A level epsilon A, level epsilon B, and so forth. So, lattice consisting of A and B atoms, A, B, A, B, A, B. And now we will see the difference between one thing. In the previous case here, even though I didn't say when we were discussing this one or this problem, the crucial thing to obtain the linear splitting was the original resonance conditions. All the levels were just the same. if you have two potential wells, forget about the end. Consider only this and that. And switch on tunneling. You'll find out the correction to each of these two levels will be of the second order, not linear. It will be small. Which means that if you are out of resonance, the quantum motion does not lead to substantial changes in the final picture. If you were localized here, you will stay localized here, almost with the same quantum numbers, with the same values of the energy and so things like that. And you are not delocalized. You will be here most of the time, very rarely jumping as a fluctuation from here to here and come back immediately here. Whereas if you are at resonance, the time spent here and there is of the same order. It's also another interesting problem to calculate, to compare these times. Okay. So this is the case when there is a finite shift, discrepancy between the two levels, and the question is how this difference epsilon A minus epsilon B compares to the hopping amplitude. We will consider both cases. The case when this is a large quantity and the case more interesting when it's a small quantity. In both cases we'll find out that at half filling, when the band is half filled, in other words, when there is on average 1 electron per site, this is not a metallic state. This is a typical metal that I described here, here, here. It's a typical metal. And this will be an insulator, a band insulator. But it's not a simple band insulator. Band insulator such that in its ground state there will be an incorporated, that so-called charge density wire. It will be a kind of, not simply an insulator, but ferroelectric. There will be a huge electric field in such a system. It's a very interesting problem to solve. It will be very similar to the problem of a Néel state in the theory of magnetism, with the only difference that the transformation, the variable transformation, which we will apply, will be for fermions rather than for bosons. And therefore, in our case, it will be a unitary transformation, similar to SU2 rotation. That's all. Questions? You have questions?